This is section 3.4, derivatives of trigonometric functions. There's one and only one content objective, and that is to compute the derivatives of the standard trig functions. And before we develop these derivatives analytically, I want to first try to guess the derivatives just by looking at their graphs. So this is based on what we did in section 2.9. And in that section, we talked about how a derivative's y-coordinates have the same values as the slopes on the original curve. So on the original curve, the easiest slopes to identify are the horizontal tangent lines, so those slopes of 0. So a slope of 0 on the original turns into a y-coordinate of 0 on the derivative. So we can plot those first. And then we can talk about what happens in between these two horizontal tangents. We can see that the slope is positive and that it's steepest in the middle and more shallow toward the edges. So that means the y-coordinates on the derivative are going to be above the x-axis, and they'll be the highest in the middle of that interval. Over here, we see that the slope is negative, so we're going to have that same sort of behavior, only now it will be below the x-axis. Here we've got positive slopes, so we'll be above the x-axis. Then we've got negative slopes, we're below again. And hopefully by this point, you're starting to recognize this blue function. It looks an awful lot like the cosine curve. So we would anticipate that the derivative of sine is going to be cosine. If we look at our second one here, our cosine graph, again we'll do the same process. Everywhere there's a horizontal tangent line, we'll get a y output of 0 on the derivative curve. Between this horizontal tangent and this horizontal tangent, we have negative slopes that are the steepest in the middle. Then we have positive slopes, so we'll have positive y values. Then we have negative slopes again. And hopefully you'll recognize that this function looks an awful lot like the sine function because it goes through the origin, except sine goes the other direction. So this is actually the opposite of the sine. It got turned upside down. So we would anticipate that the derivative of cosine is going to be the opposite of sine. To prove this analytically now, we're going to have to revisit the definition of the derivative, the trig identities, and these two limits that we've worked with on our calculators. So if we look here at this picture of sine of x over x, we can see that the y-coordinates from both the left and the right are approaching 1. And on this one, we can see that the y-coordinates, as x gets closer and closer to 0, are both getting close to that origin, or a y-coordinate of 0. So if we want to take the derivative of sine, and we don't know the rule for it, we anticipate it's going to be cosine, but we haven't proved it yet, we have to backtrack to the definition of the derivative. So here's that limit as h approaches 0 of sine of x plus h minus sine of x over h. So this is my f of x plus h minus my f of x over h, and then I'm letting the 2 points collapse. When I do that, in order to simplify this, I can't just plug in the 0 because I'd be dividing by a 0, which is not allowed. So what I'm going to do is I'm going to create these limits that I do know by using my trig identities and some algebra. So if you recall, sine of x plus h is sine of x times the cosine of h plus cosine of x times the sine of h. And then we're subtracting that sine of x times 1 at the back. Now I did a little bit of color coding here to guide you in the right direction. We want to collect these two signs, and when we do that, we get that cosine of h minus 1 over h, which looks an awful lot like this limit right here. So if I group them together, I pull that sine of x out, and then I have the cosine of x times the sine of h left over, then I can use properties of limits and the fact that this sign has no h's in it, so it's independent of the limit, and same thing with this cosine has no h's, so it also is independent of the limit. I can rewrite this first expression as this one. So I have the sine of x times that limit involving the cosine, which we know now is going to be 0, plus cosine times this limit, which we see over here, is 1. If I then simplify, I end up with 0 plus cosine x or cosine x. So tracking through the algebra, we've proven that the derivative of sine is the same as cosine. So that's our first trig identity or trig derivative rule. What I'd like you to do now is try this same technique for the cosine. We want to take the derivative of cosine, and actually you can wait until we're in class because we're going to do these together, and I want you to have them in your notes when I can double check. What's nice about these rules and knowing sine and cosine's derivatives is that now we can take any of the remaining trig functions and rewrite them as sines and cosines and then use product and quotient rules. So if we look here at the derivative of tangent, we can see that tangent is the same as sine over cosine. So if I want to take the derivative of this, rather than backtracking to the definition of the derivative, I can now use the shortcuts I have developed. So that will be a low d high, which is cosine times cosine, minus high d low, and the derivative of that cosine is the negative sign. If I simplify this, I get a cosine squared plus a sine squared, and that cosine squared plus sine squared, that's one of your trig identities. If you've forgotten these, they're on that bright green prerequisite skills packet I gave you on the very first day of school, over low squared. So there's that low squared, and we have a 1 over cosine squared. Now technically this is correct for the derivative of tangent. However, you will rarely see this showing up as an answer choice. So what they've done here, and what most calculus books will do, is they convert that 1 over cosine into a secant. So we get the derivative of tangent is a secant squared. So now I'd like you to think about how you're going to apply this same process when we're in class to develop the derivative of the cotangent, and we want to end up with negative cosecant of x. Same thing here for our next rule is how do we take the derivative of secant. If I want to take the derivative of secant, I'm going to rewrite the secant as a sine or cosine, and we remember from pre-calc and algebra 2 that secant is 1 over the cosine. So the derivative of this will be my low d high minus high d low over low squared. So here the derivative of the top was a 0 and the derivative of the bottom was a negative sign. If I simplify this, I end up with a positive sine of x over a cosine squared. Again, this would be correct, but it would not be the type of derivative that shows up. So instead, they're going to split that cosine squared into a 1 over cosine times a sine over cosine, and then replace 1 over cosine with secant and sine over cosine with tangent. So I'd like you to be able to do that same sort of process with the derivative of cosecant of x. Now that we have all 6 derivative rules, we want to be able to differentiate using them when I create new functions out of trig and polynomials and exponentials. So in each of these you are going to be using the trig derivative rules, but you'll also maybe be using the power rule or the product rule or the quotient rule or some combination of them. So we're just going to go through each of these 4 and track the process. On this one, f is a product, so we're going to have to apply the product rule. So we'll have f prime, and I'm going to write a little template for us. The first one times the derivative of the second plus the second times the derivative of the first. Sometimes if you write that, it reminds you not to make the common mistake of just differentiating this one, and multiplying them together. So I have my first one times the derivative of my second plus the second times the derivative of my first. If we look at part B, again we have a product, only this time the first factor of that product actually has 2 terms. So when I do my first one, I have to make sure I put it in parentheses. I'll have the first one times the derivative of the second, that's a secant squared, plus the second one times the derivative of the first. And again, that first is going to have 2 terms, so we've got to put it in parentheses. Now, in this particular example, I do not want you simplifying. I just want to see, can you apply these rules when they're all mixed up, and just leave it as is. On this one, we can see that we've got a quotient rule and we have a product rule going on. So this one's going to be a little tricky. So we're going to start off by just setting up kind of the template for that quotient rule, which is low d high minus high d low over low squared. Now, if you notice what I did here, I wrote the stuff that doesn't change. The low doesn't change, the high doesn't change, and the low squared doesn't change. And then inside these parentheses, I'm going to go put the derivatives. So the easiest derivative is the one on the bottom, because the derivative of cotangent is just a negative cosecant squared. But the derivative of the top is a little tricky, because the top is a product, which means I'm going to have to do the product rule. So the first one is sine. The derivative of the second is negative sine. And we want to make sure that we multiply and don't think that's subtraction. Plus the second one times the derivative of the first. So we will leave it like this just so that we can see the breakdown and where all the parts and pieces fit. For our fourth version of this, we again have a quotient rule. So we're going to do r prime of t will be low d high minus high d low over low squared. So the d high is the derivative of tangent minus 1, which is secant squared minus 0. And the derivative of the bottom one, low d high minus high d low, will be that secant t times the tangent of t. Again, I don't want you to simplify here. I just want to be able to see all the parts and pieces when you're taking the derivative. With example 2, we're asking for the values of x for which a function has a horizontal tangent. So we need to remember that horizontal tangents have slopes of 0. So that means the derivative of this function is going to equal 0. So if I take the derivative, I get a 1 plus 2 cosine of x has to equal 0. If I work to isolate x, this will happen when the cosine of x is negative 1/2. Or if we think graphically, we can say that the cosine graph equals a negative 1/2. And we can see that that's going to happen an infinite number of times. But if we're smart, we realize that these two just get repeated over and over. They move the length of the period. So if we know the period of the cosine and we know what these first two are, then we can write all the rest of them. So one of the things that you can do to get those first two is you can think about the unit circle. On the unit circle, remember that the x-coordinate is the same as the cosine of the angle. So I need the x-coordinate to be a negative 1/2. If that x-coordinate is negative 1/2, then to get to it, I'm going to move pi over 3 times a 2 the first time. Then there's 3 pi's over 3 and then 4 pi's over 3 for the next one. And then I remember that those are just the first two, so I get all the rest of them by adding multiples of pi. So I can write down that x equals both of these as long as k is an integer. If we look at example 3 now, we want to write the equation of the tangent line at a given point. So every equation of a line requires a point and a slope. We were given the point already. We need the slope, which is a synonym for the derivative, evaluated at the point. So in order to figure this out, I need to take the derivative of y and then plug 0 in. So notice that I've got a product, so I will have the first one times the derivative of the second plus the second one times the derivative of the first. If I evaluate that at x equals 0, then I end up with an e to the 0 times a negative sine of 0 plus the cosine of 0 times e to the 0. So again, we're going to be thinking about our unit circle. Sine, if you recall, is the y coordinate, so sine of 0 is going to be 0, and cosine is the x coordinate, so cosine of 0 will be 1. So I end up with a slope of 1. Once I have the point and I have the slope, I can write the equation of the line, which will be y equals the slope times x minus the x coordinate plus the y coordinate. And I'll end up with y equals x plus 1. Example 4 has two parts. The first one involves finding the equation of the line when you know the point. So on this one, we've got the point already, pi over 2 comma 2. We need the slope, which will be the derivative of that curve, evaluated at pi over 2. So to find the derivative, I've got to take the derivative of 4, which is 0. I've got to take the derivative of cotangent, which is negative cosecant squared. And I've got to take the derivative of negative 2 cosecant, which is a negative 2 times a negative cosecant cotangent. Now I need to take this derivative and evaluate it at pi over 2. So this might be a little tricky because we aren't used to working with cosecants and cotangents all that much. But if we think about the fact that cosecant is the reciprocal of sine and cotangent is cosine over sine, then we can use our unit circle to compute these values. So we're interested in pi over 2, which is this angle. And we've got the ordered pair 0, 1. So sine is the y coordinate, cosecant is the reciprocal. So the reciprocal of that 1 is a 1. Square it, you still have 1. Multiply by a negative 1, you get a negative 1. Then we're going to add 2 times that reciprocal of the sine, or the y coordinate, times the cotangent, which is the cosine over the sine, or the x coordinate over the y coordinate. So if I multiply this together, that'll all be 0, and I'll end up with just a negative 1. So now I can write the equation of the tangent line will be y equals negative 1 times x minus pi over 2 plus 2. With part B, it's a little bit more challenging. We want to find the equation for the horizontal tangent to the curve at Q. So my goal is to write the equation of that line. So I'll need a point and I'll need a slope. Well, because it's horizontal, we know the slope is 0 already. The thing that we're missing is the point. So my job, or your job, is to figure out what that point is going to be. We're going to get that point from the fact that 0 is the slope at that point. So if I take the derivative of this, which I've already done up here, we had a negative cosecant squared plus a 2 cosecant cotangent. We need that slope to equal 0. And when we solve this and find out when the slope equals 0, then we will have the x coordinate, and then we'll just need to find the y so that we can write the line. So here we've got this expression that we need to solve, and I would not give you a calculator for this. So normally solving means to isolate the variable. And if we look here, we have the variable showing up 3 times. Traditionally, when variables show up multiple times, we try to get them together so that we can isolate them. We want to have that x showing up once. And at first glance, looking at this, it might seem a little hairy. You don't really know what to do. So before we throw up our hands, I want you to think about a technique that you've been using for a long time. Let's say I have an x squared plus a 3x plus a 2 equals 0. If we look at this example, I've got x showing up twice, but they are not like terms, so I cannot put them together. Well, most of you, when you see this, you know that you need to factor. The reason we factor is because when we factor, we get two factors that multiply to give us 0. And that zero product property tells us that when two things multiply to give you 0, either the first one is 0 or the second one is 0. Notice that in these new equations, x only shows up once, so I can isolate it, and that was the whole goal, was to get x by itself. So we can apply that same process to the more complicated version that we have over here. Since I can't get my x's together, my only option is to factor. So looking at this, I can see that I've got a cosecant x in both of them. And this one is a negative, so I'm going to pull out a negative cosecant x, and what will be left is a cosecant x minus a 2 cotangent of x. Now I've got two things that multiply to give me 0. So I can say that the first one is 0, or I can say that the second one is 0. So let's look at this first one. If you recall, let me scoot down here. If you recall, a cosecant gets built off of a sine curve. So I could draw my sine curve that goes like this. And I'd know that the cosecant, which is the reciprocal, ends up doing something like this. It has asymptotes wherever that sign was 0, because you can't divide by 0 or take the reciprocal of 0. If we look at that red graph, it never crosses the x-axis. So that means this one, this particular equation, is not going to give us any solutions. That means our only option is going to come from this one. Well, this one's a little tough, and I don't know about you, but I think way better with sines and cosines than I do with cosecants and cotangents. So I'm going to convert these to sines and cosines. I know cosecant is 1 over sine, and I know cotangent is cosine over sine. So now I've got two fractions that share a denominator, and I can put them together. When I do that, I have created a single fraction that equals 0. Now remember, fractions can only equal 0 if the top is 0 and the bottom is not 0 at the same time. So we're going to be looking at when 1 minus 2 cosine equals 0. That's the same as looking when cosine is a positive 1/2. So if we think about our unit circle, remember cosine is the x-coordinate, so we want positive 1/2. So we can either have the pi over 3, or I can go all the way around and have the 5 pi over 3. And then, of course, I can continue to go around as many times as I want, as long as I stop at either this point or this point. So I can add multiples of that period. So we got a whole bunch of them, and the goal was to write the equation of the line. So what we're going to do is we're going to pull back up here, and we're going to look at where that Q is happening. If we look here, we can see that Q is actually at a point that is to the left of pi over 2. So if we look at our options, the first and only one that is smaller than pi over 2 and in the positive quadrant 1 is the pi over 3. So that means our x-coordinate for the point is a pi over a 3. To get the y-coordinate of that point now, so that we can write the equation of the line, we've got to plug that pi over 3 into the function itself. And if we do that now, we can see that y of pi over 3 will equal 4 plus the cotangent of pi over 3 minus 2 times the cosecant of pi over 3. Now, unfortunately, I won't let you leave the answer like this because these are exact values that you can read off the unit circle. So we're actually going to take this to the answer itself that doesn't involve any trig when we're done. So we'll keep that 4, And then we'll look at the cotangent. Cotangent is cosine over sine. So on the unit circle, it's the x-coordinate divided by the y-coordinate. And if we go to pi over 3, we can see that the x-coordinate is a half and the y-coordinate is this root 3 over 2. So we would have the x-coordinate over the y-coordinate, and dividing by that fraction is the same as multiplying by its reciprocal. And if we do the next one, we're going to have 2 times the cosecant, which is 1 over the sine, or the reciprocal of the y-coordinate. If we simplify this now, I'll have 4 plus 1 over root 3 minus 4 over root 3. So that's a minus a 3 over a root 3. And we could take it even further and rationalize that denominator. Not that you'd have to, but you need to be familiar with the concept so that if I do rationalize, you can recognize it when you see it. And we'll see that we get a 3 on the bottom and a 3 on the top that will cancel. So we get a y-coordinate of a 4 minus root 3. Once we have the point and the slope, we can write the equation of the line, which is y equals 0 times x minus the x-coordinate plus that y-coordinate. Since the slope was 0, we could just simplify and say y equals 4 minus root 3. And that will be the equation of our horizontal tangent line.